another level. We're going to explain the steps of solving an equation. We're going to write the thought process down to our steps. Okay? That will get you ready for proofs in geometry. You start explaining the mathematical steps. Okay? You're also going to be writing equations from real life examples and then solving. Okay? So you guys probably know the motions. We're going to take it to the next level. Okay? Just because you know the motions doesn't mean you should shut down and get frustrated. Okay? Work with what we're doing. Alright? Sound good? Okay. Skill 3-1. Combining like terms and distributive property. That's the first skill. Okay? What you're going to have you do is you're going to read page 100. You're going to look at examples 1 through 3, 5, and 6. Now you don't have to copy those examples down, but I still want you to read through them, see what's going on. And then you're also going to do the vocab on page 102. There's 4 vocab words. Alright? 4 vocab. I want you to have those written out the best you can. Any questions on what you need to do in the next 10 minutes? Okay, again, this is nothing new. We've done this before. Alright? Alright, so what do we read about?
Distributive property combined like terms.
Okay, distributive property combined like terms. Let's talk about like terms. Tyler? Like terms. What are they?
When the same variable is raised to the same power.
Okay, good. Values with the same variables raised to the same power. Okay, so say we have these values. 5x, -3, x squared, -x, and +6. Okay, we've got 5 guys up there. Tyler says variables with the same powers are like terms. Or, do you think you could come up here and underline some of these values that you think are like terms? Feel pretty tough today?
Nope.
Okay. Anybody think they can come up here and underline? All right. NASCAR fan. Okay. We agree with the spleen?
Yes.
Yeah? Why do those go together? It says like terms have the same variables with the same power. It doesn't have a variable, so if they don't have a variable, they automatically go together, right? Is that it? If you have numbers up here that don't have variables, they are like terms. Is that what you're saying?
I think that's what I'm saying. I don't know.
Well, it's not about the numbers having exponents, it's about the variables having exponents. So the first thing we look at, do they have variables? Does -3 and 6 have variables? No. So should they go together? Yes. Yes. Perfect.
Well, I didn't know. They're kind of scary.
It is getting closer to Halloween. Good. Anybody else think there's any other like terms up here? Miss Neal? Oh, like quarterback letter across the 5x? Okay. Ooh, even double line. Ooh. Ah, fumble. What about x squared?
Isn't it the same thing though? Because x times x is x squared.
Isn't x and x squared the same thing?
Wait, so could you like divide it into two, like x and x?
Yeah, so
Yeah, you can.
it's multiple.
Because y
Still
times
not, it's still not the same. Remember, what is like? What is it? What was the definition for like terms? Okay.
Raised to the same.
Austin, say it again.
Same variables and the same power.
Same variables with the same power. Do these two variables have the same power as this variable?
No.
No. So are they like terms?
No.
No. This guy right here, he's alone. Sitting at home.
that is a horrible triangle.
It's not a triangle.
It's an obese
Shush
triangle.
them about. Okay? So, what is the exponent for these x values? What is the exponent for those x values? Audrey?
What?
1. Remember, when there's no number there, it's automatically 1. Just like the number out in front. We don't have to show it. Okay? We don't have to show it. Okay? Vocab check. Jasmine. The numbers in front of the variables, what do we call those? Numbers in front of variables. Coefficients. Okay? What's the coefficient of this x? What's the coefficient of this x?
5.
5. What's the coefficient of this x?
1.
Say it again, Hannah.
Negative 1.
-1. Remember, is there a number there? Well, what number should we put there? 1. What type of 1 is it? Okay, good. What's the coefficient of x squared? 1. Okay? 1. Okay? What do we call 3 and 6 when there's no variable with it? It's a constant term. That number will never change. Will this number change? Yeah. Put in 3 for x. What does this number become?
3x. 15.
Okay, listen again. If I put 3 in for x, what will this number become? Everybody.
15.
If I put 4 in for x, what will this number become?
20.
If I put 6 in for x, what will this number become?
30.
So, does this value stay constant?
No.
No, it changes. That's why we call it a variable. It changes. No matter what x is, will this number ever change? If x was 5, what's this number going to be? If x was 7, what's this number going to be? That's why it's constant. That's why we call it a constant term. It never changes. Okay? So those are some examples that can help you out with your definitions. Okay? So I want you to try this on your own. I'm going to put up some terms. I want you to tell me who's like and who's not. Here we go. 17. Negative 3x squared. 5x. Negative 11x. 4x squared. So go ahead and put shapes. So if you find 3 alike, all 3 should have a triangle. Or if you have 2 alike, all 2 have a circle. That's how I want you to identify who's alike. Okay? So, Austin, give me 2 or 3 or 4 or however many like terms.
Negative 3x squared and 4x squared.
Good, let's go put these in triangles. Whoop! Those are like terms. Logan, why are those like terms?
Because they both have x squared.
Good. They both have a variable with the same power, x squared. Very good. Price. Give me some other like terms.
5x and negative 11x.
5x and negative 11x. Good. Spleen. Yo. Why are those like terms?
Because they both have a number and a variable.
No. Because this has a number and a variable. Are these like?
Well, that one has an x.
So So they both have a variable with the same exponent, same power. What's the power for this x? 1. Okay? That's why these are the same. Okay? Does this 17 have any friends, Juan?
No.
Nope. He's by himself. All by myself. Okay. That is to a song. Okay. Why do we care about who's like who? What's the importance of knowing these two are like terms? Jonathan? So we can combine them. You can only add and subtract like terms. You can only add and subtract like terms. You can only add and subtract like terms. If I say it 3 times, what does that usually mean? Write it down. Let's keep him awake. He's bright-eyed and bushy-tailed. Okay?
Mr. Smith,
Yo.
can I switch seats?
Why?
You're annoying me.
You're distracting me.
Gentlemen, are you having a hard time being non-chatty Cathy's? Huh?
What?
How about we zip the lip back there? Okay? Can you do that?
Right.
Well, if you don't, you can go be chatty Cathy with Mr. Manon. So how hard are you gonna try? Are you gonna try really hard?
Sure.
Okay. So, be quiet. Think. Zip the lip. See if that works. Stop laughing back there. I'm talking to you, Ward.
I'm not laughing.
Yes, you are.
And now I don't know if it's Ward or Ken. Now I think it's you.
Yeah, really.
Alright. So we're going to combine. So, this is our next example. We have -4 plus 3x minus 5x plus 6. Hold on, we'll get there. Just patience.
Do I have to equal them?
Just patience. Hold on. Just, I just want you to sit there. Your question will be answered. Okay?
Do I have to
Shh.
circle? No.
No, you don't have to circle. You're okay. Stop. Just right there. Okay? Your question will be answered. I promise. Okay? So, are we evaluating this expression? First of all, why is this an expression? What makes this an expression, Mackenzie? There's no equal sign or no inequality. That's why this is an expression. Very good. What would you do forced? What would you do forced, Sid? What would be the first thing you do?
Underline the like terms.
Okay? We could do that, but there's something else you want to do first. Audrey?
Change the subtraction to a plus symbol.
An addition?
That.
Okay? We want to change this. We want it to be all addition. Okay? So I'm going to change this to a -5. Now you're probably thinking, well, why? Why does that matter? You guys can identify the like terms right away, right? You can say, oh, I know who those are two. Are all the like terms by each other?
No.
No. Wouldn't you like them to be by each other? So you would want to switch the order, right? You'd want to change the order of this problem, correct? Can you change the order when it's subtraction?
No.
No. So that's why we have to change it to addition. Okay, does that make sense? In order to change the order, it has to be all addition. So now, what do you think we're going to do? Change the order. All right, Mrs. Jones. Why not Mrs.? You're a miss. Miss Jones. What would you like to come first? How would you like to rearrange this?
The variables in back and the
Okay, so tell me what to write down.
okay, -4 plus 6.
Okay? Well, these are two children. They're naughty. They're naughty children. You know what happens to naughty children? No. They get grounded to their room. So these are my high school kids. They're grounded.
I have to eat, so.
Shh. They get grounded to their room. Well, who else am I missing?
The mommy and daddy.
No. Preschoolers. See, these are diapers.
They get put in
Yes.
the corner.
They have to go to their own room, right?
No, the corner.
You can't put preschoolers who are in trouble in the same room with high schoolers who are in trouble, right?
All that.
It just be mass chaos. So we put them in separate rooms. Associative property, grouping. Right? And Lon, you're a bright man, right?
Yeah.
What separates two rooms? A wall. What's going to be our wall in this scenario? An addition symbol. Because, just like I was saying, can you put two high schoolers together? Yeah. Can you put two preschoolers together? Yeah. But can you put a high schooler with a preschooler?
Yeah.
No. Bad. Don't do it. Okay?
Then they give a baby.
So, listen up. Listen up. What we're doing is we're changing to addition so we can rearrange the order and we can group. All right? What do I get when I add these two together? What's -4 plus 6? 2. Positive 2.
So what does that make it now?
Okay?
I know.
Don't worry about it. That example's over. That example's over. Okay? Shh. Listen up. Listen up. How do I add those? Do I get? I mean, what would you get for your answer there?
-2x squared.
Is it though?
No.
Why not? Why is it not -2x? So you guys are saying this should be a -2x, but not -2x squared.
Yes, because you're not multiplying them, you're adding.
Ah. Does that make sense? Shh. Is x plus x x squared? Or is x times x x squared?
X times.
I agree.
X times x is x squared. So who are we really adding? The inside or the outside?
Outside.
Oh, who was that like?
Thing.
The what? What did, hey, right here. What did we do last week?
Radicals.
Math.
We did radicals. We added and subtracted radicals, right? And in Austin, did we add the inside of the radicals? Did we add the inside of the radicals?
No.
No, we added the outside. So that's why you have the outside, the coefficients. And that's how you get 2 plus -2x. Now, could we have written it the other way?
Yeah.
Yes, because when we have addition, what does it matter? Order, commutative property. Order doesn't matter. Okay? Sweet. Any questions on how to add like terms? Good in Mr. Rogers' neighborhood? Awesome. Moving on to the next example. We're going to talk about the distributive property. The distributive property. We've talked about this before. A couple weeks ago. Remember in our properties frame?
Yeah.
What was our little verbal saying for distributive property? It made the blank disappear. It made who disappear? Who said it? It made the parentheses disappear. It made the grouping symbol disappear. So first of all, we have to have a grouping symbol. Well, parentheses are a perfect grouping symbol. Okay, we want to simplify that expression. We're going to use the distributive property to simplify. Okay? One quick tidbit. Remember back in the first day, I said we use order of operations to evaluate and to... Isaiah, say that louder. I want you to write that down again. We use order of operations to evaluate and to simplify. Okay? Because we're simplifying, so we need to use the order of operations. That's very important when it comes to combining like terms.
Wait, what was the order?
You use order of operations to evaluate and simplify. Okay? Alright, so get back here. Andrea, kind of off by yourself today, I'm sorry. How is this 3 connected to the parentheses? Multiplication. But is the 3 really connected to the parentheses? Who's it really connected to? The stuff inside. Who's all inside here?
2x.
And 1. So we need to multiply this 3 by the 2x and the 1. But what should I do first? Do we like subtraction?
No.
Who do we like better?
Addition.
Change it to addition. I'm telling you, if you change everything to addition first, woo! Life will be great. Life will be fantastic. Okay? Now, we need to multiply what's on the outside by everything that's on the inside. The distributive property is you multiply what's on the outside by everything on the inside. The distributive property is you multiply what's on the outside by, oh, you missed a key word, everything on the inside. Okay? So I'm taking this 3 to the 2x and 3 to the negative 1. So this is what it's going to look like. 3 parentheses 2x here plus 3 parentheses negative 1. Am I multiplying 3 by everything on the inside here?
Yep.
Good. Lane, you look like a smart man. What's 3 times negative 1?
Negative 3.
And I was correct. You are a smart man. Well, how am I supposed to do 3 times 2x, Hannah?
You just multiply it out, and you just multiply 3 times 2.
So you're saying the answer should be 6x?
Yeah.
Oh. How can I be sure of that? How can I prove that she's correct? How can I prove that, hey, she knows what she's talking about? Using something we already know. Any ideas how we can show that she's right?
Addition?
You're thinking on the right track, using some sort of operation. Addition's just, or multiplication is just advanced addition, right? Here's what I'm trying. 3 times 4. It's kind of like 3 times 2x, right? Pretty similar. How would you rewrite that as an addition problem? Any ideas? Raise your hand. How would you write 3 times 4 as an addition problem? Or?
3 times 3 times 3 times 3.
Okay, could you do it the other way too?
4 times 4 times 4.
So really you're saying 3 groups of 4, and you're adding them, right? Is that what multiplication is? So, Ian, how would I write 3 times 2x?
2
Is that what we did here?
Oh, 2 plus
But the whole thing. 2x, keep going.
2 plus 2x
Okay?
plus 2x.
Oh, and haven't we added this? Haven't we done that type of addition? Who do we add? Do we add the inside, or do we add the outside? So 2 plus 2 plus 2 is 6x. We just proved that Hannah was correct by using something we already knew how to do. Okay? So Hannah is right. You're taking the 3, you're multiplying it just by the 2. Okay? That's why it's not 6 plus 3x. I've heard that answer multiple times before. Okay? So, this is your final answer. Any questions on anything we've done? Is some of this kind of a review? You've done this before. Has there been some new stuff you've been kind of introduced to? Maybe some of the vocab, constant term, coefficients. Okay? Everyone's going to be a little different. I know that. Some people may, okay, I got this, I know what I'm doing, let me go. Others of you are like, oh, I kind of forgot that. Homework. Page 103. Numbers 19 through 35. And 49 through 69. All odds. We're doing all those of the odds. It's about 17, 18 problems. Should take you about a half hour. I want to see the work. I want to see this right here. Everyone watching? I want to see this. And for the distributive, I want to see this.